Hello, everyone. Good morning, good afternoon, good evening, wherever you are, and welcome to the second week of the Chain Fusion Hackathon. We have a very special demo workshop today on the topic on how to interact with EVM chains using the EVM RPC Canister. And I'm going to quickly invite two of our speakers today, Grégory and Ihor, to the stage, who will walk you through everything in a bit. In the meantime, make sure to say hi in chat. Make sure to post all of your questions in the questions area on the bottom right side, as well as the chat section where you will be able to voice anything that you have on your mind. In the meantime, as always, all of these workshops will be recorded and made available to you in the shortest time span possible, which probably will be within the next 12 hours. And you will be able to rewatch everything recording as well, and formulate any additional questions. For such, make sure to post on our Discord. As you all know, if you have not joined already, please make sure to head there and post your questions with everything Hackathon related, so we can help you out, or at least forward your questions to the parties that can answer them. Welcome, Grégory and Ihor. And for those of you watching, start off with Grégory, and we'll continue on with Ihor.
Hi, everyone.
Hi.
I'm Grégory, a software engineer from the DFINITY Foundation, working on the cross-chain team. And so today I would like to present a bit how to interact with Ethereum on the internet computer. So I will share my screen.
Yes.
I have a few slides. But not much. Okay, please shout out if you don't see my screen. I will not, because I only have one monitor, so I will not directly see your questions if you have any. So if you do have questions, please feel free to interrupt me at any time. So the idea here is that we'll have a couple of slides to set the stage, and then quite rapidly, also depending on your question, we'll dive into a basic example and into some small demo and look a bit more in detail at the code. And afterwards, Ihor will dive in a bit more details about the EVM RPC Canister itself. So without further ado, let's start with a famous quote from the Ethereum white paper itself. So I'm assuming that maybe you have some familiarity with Ethereum, and maybe not as much as with the internet computer. So with that in mind, basically, like Ethereum itself presents itself with the initial motivation of being like a general compute platform on blockchain. And the point of the internet computer is that, Ethereum does have some limitation. For example, you cannot host front end directly on the blockchain, etc. And the internet computer aims to solve that and to have everything on blockchain. So, in case you don't know, basically this is the stack of the internet computer. So from a very high level, the internet computer is more or less, you can view it as a sharded blockchain organized by so-called subnet. So those are more or less like kind of somewhat independent blockchain where you have a single root of trust. So at the bottom layer, you have like independent data centers from different companies all over the world, so different countries, different continents. Those data centers are connected via regular internet protocol, so the IP. And then each machine run the internet computer stack. So it's like basically you can view it as an OS image. And then each of these machines run various so-called canisters. You can view it more or less as a smart contract, which is compiled to WebAssemblies. So you can write your smart contract in Rust, for example, which is what I did for the small example that we're going to see. But there are other languages as well, like Motoko or JavaScript and so on. Basically, anything that can be compiled to WASM. And this is run in a replicated manner. And this is what gives you like the security guarantees of the internet computer. So this is like a very high-level 30-second overview of what the ICP is. And basically, if you want to use the ICP to talk to Ethereum, there are like two pillars of the Ethereum integration. The first one is threshold ECDSA. So with the internet computer, your smart contract can sign securely messages via so-called threshold ECDSA. So the idea is more or less that each canister on its own, so each replica in the subnet. So let's say you have like a 40 nodes subnet, for example. Each replica has a share of a private key and can use that share to sign a message. And then those signature shares will be transmitted via peer-to-peer protocol. And once you have enough shares, you can reconstruct like a perfectly looking ECDSA signature. So basically, this allows that there's like no machine at any time knows the private key. So the private key is shared among the nodes of the subnet. And this is like what allows, for example, a canister to hold an ECDSA public key and hence a corresponding Ethereum address, and to use that public key and the corresponding share of the private key to sign messages on behalf of the canister or of the user. So that's what allows, for example, to send Ethereum transactions or to create Ethereum transactions. And then the second pillar, so now we know basically how to get how to derive an Ethereum address, how to sign messages, but we need to transmit it to the Ethereum blockchain. So we need somehow a way to contact Ethereum. And the second pillar there is HTTPS outcalls. So a second feature of the internet computer is that Canister smart contract can reach to the HTTP world, so web to world. And so in particular, you can use that feature to contact, for example, Ethereum JSON-RPC providers. So you can use those providers to read the state of Ethereum, for example, transaction count of a given address or ETH balance, etc. Or you can also use those providers to write to the Ethereum blockchain by, for example, sending a signed transaction. Right, so those are the two pillars of the Ethereum integration. And I don't know if there are any questions. Okay, not so far. So I will keep talking. And now, so we're going to see a little example. So it's in the example repo. Okay, you have the link below on the slides. And basically, the idea is that of this little example is that to have a canister which is hosted on the internet computer, and it can derive like for each user a different Ethereum address, and each user can then contact that canister to send ETH to another Ethereum address. And so basically, the structure of the project is shown on the left. So this is a canister written, for example, in Rust. It could have been written in some other language as well. And yeah, I don't know your familiarity with canister development, but basically, the thing on the source are like, let's say, your standard code. And then there are like two files which are, let's say, specific to canister development, which are the one highlighted below. So there's the candid interface. So this kind of a specification of the interface of your canister. So for a client, how to contact that canister and how to interpret its response. And this DFX JSON is basically tells how to build your canister. So for example, using cargo and WASM target. So let's dive in a bit. I hope you can see my IntelliJ. So this is, for example, the DID file I have opened. And the most important thing there is the service declaration. So this is where I define the methods which can be called from a client. So for example, there, this method, Ethereum address, the goal is to derive for a given principal an Ethereum address. So we can call it right now. I already deployed it. So please tell me if my shell is not readable. I can make it bigger.
It's perfectly visible, by the way. So
okay, thanks for letting me know. So basically, what this thing does is I can call this method, for example, dfx. So dfx is a command line tool to interact with canisters, and say, okay, I want to call a method. This is the name of my canister, and this is the name of the method. And there I can provide an optional argument. I didn't provide an optional argument, so here the semantic in that context is that it will take my current principal, which is that one. So principal identifies the user on the IC, right? And so for that principal, my canister derives that Ethereum address. So now we can check if there is anything already on that Ethereum address. So by the way, the canister was deployed to target the Sepolia blockchain. So I can see now I have this address there, and there's absolutely nothing there. So to start to be able to play with it, I can send it some ETH, so some Sepolia ETH. Right, so with the wallet of your choice here, for example, MetaMask, but right, so now it's going to be mine at some point. And so basically, now the goal of this little canister is, okay, it's going to get some ETH to that address. And now I want to be able to send some of that ETH somewhere else. So that's the method there, send ETH, where I can say, I can target another Ethereum address, and I can specify a certain amount. And so this will create an Ethereum transaction and send it via HTTP outcalls. And so one thing that I assume you know about Ethereum is that transactions are ordered, right? So there is a transaction count for a given address. So in particular, if we want to create a transaction at some point, we need to be able to know, like, okay, for a given address, how many transactions were sent from that address before, so that I can derive the nonce for the next transaction. And so that's why also for this, there's this little helper method there, transaction count, which going to contact the HTTP outcall, the Ethereum blockchain, to ask how many transactions were sent from that address. So I can also do it here. Right, so I have a couple optional arguments which I don't specify, and what this means here is that, okay, what's the transaction count for my Ethereum address? So for this principal, and if I didn't specify the block height there in the canister, it says, okay, transaction block height finalized. So at finalized block height, my address didn't send any transaction, which is correct because so far this address didn't send any transaction. So now my transaction was received. So this address has some funds to play with. So let's try to send one way, back to okay. So now I will try to send just one way. So way is the base unit of ETH, and this is my MetaMask address. Just to be sure, I can copy paste it. Okay. So basically, this will create an Ethereum transaction. So following the EIP 1559, try to sign it via threshold ECDSA for the key derived from my principal, and send it via HTTPS outcalls. And for example, here, I get a transaction hash afterwards. So Right. So we can see that this transaction was already, sorry, let me, just to be sure that I have the correct transaction. Yes, this transaction was already mined by the network. So I can see that now this address sent one way back to my address, right? And if you look at the detail of the transaction, like nothing tells you that this transaction was actually issued by a canister on the internet computer. This is like a perfectly normal looking ECDSA signature and sign statement. So now, unless you have questions, I would like to dive a bit more in the code itself. So this is basically what this little canister does, and we can look a bit like behind the scenes, how it's organized. So so basically the main file is this, and this is where I define like the top level method. So for example, this method Ethereum address corresponds to that method Ethereum address declared in my interface file, and the same thing for the other ones, right? So I can initialize my canister with various arguments, and basically there are two things which I can use. One is to say, okay, whether I want to target the Sepolia network or Ethereum mainnet. So currently we are using Sepolia. And second is the type of ECDSA key that I want to use. And basically there are three different types of ECDSA you can use. So the production one, which you can use on mainnet. There's also a test one, which you can also use on mainnet. And then there's a local development one. So if you deploy your canister locally on your laptop, you can use this key to compute ECDSA signatures. But if you deploy your canister on mainnet, then you should use one of the two. So basically, this little init is just to initialize the state of my canister, and the state is just saved in some variable state. So this is just like this just stored like these two pieces of information, right? And now we can dive it a bit more. So for example, how to derive an Ethereum address given a principal. So basically, this can be called by any user. And one thing to check is, for example, that the user is not anonymous. We want a principal to derive an address. So we allow, for example, the user to specify another principal. So for example, if he wants to send funds to a friend, then he needs to know the Ethereum address of that friend. Or maybe he wants to know his own address like we did, and then he doesn't need to specify anything. Right. And so basically now the whole logic of deriving an Ethereum address is hidden behind those two lines. So let's go and see what it does. So basically the idea is, so canister is going to get threshold ECDSA public key, and then we can use that public key to derive additional public keys following the BIP32 standard. So we can derive a family, like a tree of subkeys deterministically, and that's what this does. So here we assume we derived the public key from the canister. This uses more or less the interface of the internet computer to get a threshold ECDSA public key for the canister. And then I can use a derivation path to derive a new key. And so, for example, one possible way to derive a key for a given principal is this. I have a derivation path, and I put more or less the principal in byte form as part of my derivation path. and that's how I get my key for that user. Of course, this is highly application dependent. You may have more complex strategies. For example, if you want to allow maybe also sub-account for the principal, so that you have different addresses for a given principal, etc. But here, this is really like a bare bone example. Right. So this part is just about kind of deriving a key given principal. The second one, for example, getting the transaction count for a given address. So here, one interesting thing is we're going to use HTTPS outcall because we need to get data from the Ethereum blockchain. So, and here there's one cool thing, for example, this part, which is the EVM RPC Canister. So that's a service that's already deployed, and I can use that to query data on the Ethereum blockchain. So for example, here, I just use that canister, which is already deployed, to retrieve the transaction count. And one thing we can see, maybe we didn't see the log, so let me do it here. I hope the shell is big enough. Let me make it a bit bigger. Right, so I do the same transaction count call, for example, as we did before, but we're going to see a bit more logs now because I deployed locally in that shell. And so we see, okay, so we can see more logs. In particular, we can see the logs of this EVM RPC Canister, which I deployed also locally. And basically, what happened there is that we can see that the EVM RPC Canister is, for example, querying multiple providers for us out of the box. So this you can of course change yourself, but by default, the EVM RPC Canister is going to query multiple providers so that you don't have a single point of failure. And then the EVM RPC Canister is also going to give you like a consolidated response. So more or less, if the responses are equal, it's going to tell you, okay, transaction count is, for example, 0. And if they are not equal, then the canister will give you back all responses that it got. And it's up to your application to decide what to do with that. For example, to try to do some different strategy for reduction instead of equality, doing median or other stuff, or just simply failing in that case. All right, so here, basically, this basic example, the whole magic of getting transaction count is hidden behind the EVM RPC Canister. So here it's very easy to read stuff. Right, and so finally to send if. So here there are basically two things happening. Right, so we need to create a transaction. So an Ethereum transaction for example, the EIP 1559 standard. And we can use here any library that we like. So for example, here I used Alloy, I think, but you can use other library, it doesn't matter. And so for this, we need like to be able to build that transaction, we need several information. So one is this nonce, which I mentioned before. So we need to get the transaction count of the address with which we want to send the transaction. This will correspond to the nonce. In a normal application, you would also need to estimate the current transaction fees. So if it's a standard Ethereum transfer, then the gas limit is clear, it's 21,000 gas. But the other parameters like max fee per gas and max priority fee per gas would be dynamic and would depend on current network usage. And right now, this little basic example of mine is very stupid. Everything is hard-coded so that with some generous constants, so that most of the time it should pass. But of course, in a real-world application, you will need to retrieve the fees, maybe do some caching, and maybe also do some complex logic to handle the result of various providers, etc. But this part there is abstracted away for this very basic example. And so basically, once we have this, we can have a transaction object or a transaction struct. And now we're going to sign that transaction struct So we're going to call the threshold ECDSA API of the Internet Computer, which we can see here. So basically, I have my key for that user, which I derive via the same derivation path as before, and I can call the ECDSA signing API to sign the statement. And one little tricky part is also so this the signature from the Internet Computer doesn't give you the recovery ID, which is needed for Ethereum signature. So we need to additionally handle this, but yeah, this is still possible via some off-the-shelf library. And once we have this, we have the full Ethereum signature. And now we can basically send our transaction. So now I have the sign statement there, and now I can send the transaction. So here there's one thing to note. So, right, so we are sending a transaction, so it's a signed statement. So now basically it doesn't really matter to which RPC provider I'm sending that transaction because it's signed, so the RPC provider cannot change the transaction. But that RPC provider could be down or could try to do a denial of service and etc. So to avoid kind of any single point of failure in a real world application, you would maybe use like multiple RPC providers also to send your transaction, or doing maybe some round robin strategy or etc. Right, but here for simplicity, I just use one RPC provider to send the transaction, and that's about it. And yes, and one thing to note there, so we are sending data to the Ethereum blockchain, so we are writing to the blockchain, right? It's a non-idempotent operation, and with HTTPS outcall, this is a bit tricky because those calls are replicated. So each node, so for example, if I have a 40-node subnet, each node is going to do that call. So each node is going to send my transaction, and so of course it's kind of expected that if the transaction is correct, one node will receive an OK result from the JSON-RPC provider, but the other nodes most likely will receive an error of the type, hey, we already know that transaction, or the nonce is too small, or stuff like that. So the EVM RPC Canister tries its best to kind of simplify the error, but it's a bit brittle because the errors in Ethereum JSON-RPC are not specified, so they depend basically on the implementation of each EVM client. So if you see an error there, it doesn't necessarily mean that your code failed. The best way to check is to check the transaction count for that address, or to see in a blockchain explorer like Etherscan if your transaction hash is known or not. All right. So now I'm almost done. This we did, and basically here are a few links for what I explained, going like from high level to the lower level. In particular, what's most likely relevant to you is more details regarding the EVM RPC Canister. So in this basic example, we saw how to use that in a very basic manner. That should give you a head start. And I think Ihor will continue with more details regarding the EVM RPC Canister.
We have a question from Kartikeo, who's asking, can you suggest some project ideas, a tool or part of infrastructure that you would like to see made during the hackathon?
Well, I would say, yeah, it depends what you want to focus on. But there's some cool stuff, for example, I don't know, being able to contact any ERC20 contract, or be able to contact any type of smart contract on Ethereum from the IC, I think could be a good showcase. For this, you need to basically know the ABI of your smart contract and kind of encode things on the fly and so on. Could be interesting. We have like, I mean, from experience, we have a limited set of, we use a limited set of features, for example, with the CK-ETH minter and CK-ERC20 integration. But of course, Ethereum is much wider than that, right? So you could also use, for example, DIC to interact with smart contract on Ethereum, which would need, for example, otherwise an oracle or anything off-chain. DIC could provide such functionality. Yes, just on top of my head.
There's a question from Slavic in the questions area who's asking, how can a unit test Canister with Chain Fusion locally?
A unit test. So basically, I would say, like, generally you would want to organize your code in such a way that anything that's IC specific is very isolated. One way to do that, you could introduce a trait, for example, for the management canister interface, so that you could have two implementations thereof, the main one that used the management canister interface at runtime, and another one for test that used a mocking framework. This allows you to be able to test your logic fairly independently of anything else. You can also have high on the stack integration test with like a state machine framework or Pocket IC framework. This can give you more confidence regarding more kind of end-to-end, I mean, not end-to-end tests, but you will have more like all the candid encoding and decoding, for example, stuff like that. But I would say usually what you want in terms of testing, right, is this nice pyramid, right? So as many unit tests as possible. For this, you want to basically put everything that's IC specific, fairly isolated from the rest, and then have a few integration tests as you see fit. And yeah.
Perfect. Ihor, take it away. Grégory, I'll move you to the backstage as well.
Yeah, hello everyone. So thank you so much for the invitation. Happy to be here. And thanks, Grégory, for his amazing presentation. I'm really excited to see how ICP Chain Fusion feature can empower like different dApps built on top of ICP and provide like cross-chain potentiality improvements to different chains. So yeah, let me share my screen. So yeah, my name is Ihor, and we with the team built modular on-chain Oracle solution on top of ICP and provide real-world data to different EVM compatible chains. So we utilize different like great features of ICP, like ECDCA threshold for generating the proofs and making signing a transaction to send to different chains. Also HTTP outcalls to send those transactions to different RPCs, and so on to make it fully built fully on chain. Also, we utilize like Heartbeat system to make an execution process, build like random tape for generating randomness and providing that, and different things. So if like we focusing today on EVM RPC Canister, and yeah, let's move on. So why in general, why it's created? In familiarity to exchange rate canister, it's another like super powerful canister which DFINITY implemented and launched on like permissionless way to the whole, like it's controlled by NNS government, and it provides a lot of power to different canister built on top of ICP to utilize already existed like well refactored and efficient code which utilize different sexes to provide price feeds, for example, from different sexes, and you can utilize it on chain. And in the familiar way, they implemented like EVM RPC Canister to simplify interaction with the different EVM chains. So it is like different pre-built chains like Ethereum, Sepoila, Arbitrum, Optimism, and the base chain, but also you can utilize any other EVM by yourself, specified it as you need to. So that like one of the features that you don't need to hold API keys, because when you hold even on like Canister API key, it potentially could be vulnerable and validator on this replica where your canister is working could access your API key. So instead of this, EVM RPC provides this possibility to pay by cycles on the canister, and this canister already have some like partnership with under the hood different RPCs connection providers, which allow exactly from this canister make different calls. So it's really like pre-deployed and high efficient code, which with easy like just JSON RPC API, which most common and most friendly that you can just utilize it. And it gives power for creating different like cross-chain application, which could help, for example, EVM chains or interact or create in general like chain fusion with the like proofs from everywhere, cross-chain messaging, or like oracles, or any type of cross-chain DEX and so on. And it's fully permissionless. So the main idea about like this ECDCA threshold, for example, and is HTTP outcalls, and that you can build it fully on chain. The main idea is that it's fully permissionless, and like nobody will be there is no single point of failure, and nobody will be able to manipulate it and control it. So but it's controlled by NNS government, so it could be like updated or delivered in different way, or just be improved in continuously improved way. So how it's working? It's utilizing under the hood different RPCs partners, and like making it multi RPC way, and provide like common JSON RPC API from canister to different canister who can interact with, and different methods like get logs, get transaction receipt, and send raw transaction. So firstly, if you want to execute to some transaction from your canister on ICP on Ethereum, for example, you are like preparing it, and then signing with ECDCA threshold, and then sending to this already signed transaction to EVM RPC Canister, and it's delivering already through different multiple RPC connection to final chain. Second, the most important thing that HTTP outcalls allows in general to communicate with RPCs fully on chain. When it's when you're triggering some HTTP call, it's happening in that way that this HTTP request happening from all each validator in this replica where your canister is hosting, the same request happening from each validator, and when the same responses is getting on each validator, you're reaching a consensus, and you can utilize this data, or in general, like it's successfully transmitted to other RPCs. So yeah, it's controlled by, as I mentioned earlier, by NNS government. So just like ICP community can control every like a canister and improvements and updates on top of that. And integrated RPC under the hood, it allows you just firstly you will be sure that if one RPC won't work, another one will be used, and it's really like more comfortable to just pay in cycles instead of like different API keys which you need to top up and so on. So it's just in a small example how you can like ask EVM RPC to get some logs from some EVM chain. So you can just provide like address, different like range of the block. Topics is just like signature of encoded signature of your method of your event, and then just index it, encoded indexed parameters of your event which was executed there. And actually we in our product utilize it a lot. And how we are utilizing EVM RPC Canister. So basically our solution, it's an Oracle solution, it's modular solution which allows different EVM compatible product to build their own custom data feeds. So we are focused mostly on customization, and we focus on providing custom data feeds and other like verifiable feeds, for example, like other chain data information which could be verified and verified on another chain, or like more different tools. So we have different modules which could be combined in different ways together and provide your like super customizable way to deliver any type of data. For example, if you have like a derivative protocol or like prediction market, you mostly like those products just start researching Oracle market and how they can solve this problem, realizing that there is no actually Oracle established Oracle in the market which could bring you like custom data, and they start building their own off-chain services for such thing. And we focus on helping projects like that to avoid off-chain services and utilizing those features altogether. So CBO is fetching mechanics. It's fetch different data from, for example, taxes for price feeds, but it also could be utilized for custom data feed that product can provide different sources from real world or from where it should be fetched. Also, it could be created by some DAO on different chain or DAO or by NNS, provided some custom feed, and then all other like product can utilize it in different ways. Also, this module help to make a pull Oracle model. So pull Oracle model, it's when it's efficient and on-demand model when you need to deliver some data to your smart contract. You can ask for example, from front-end side of your application, and it will be like dynamically fetched only new data, and our Canister generating a proof that no third party which delivers this final like transaction data to your smart contract cannot manipulate it on the raw, and it could be verified on chain and utilize it in different way. But also we have a automation tool in combination with the data delivery tool. It start being like a push Oracle model. So you can just set up like regularity or different asset volatility that will be executed and provide data to your smart contract or on regular basis. And it's everything executed by like AK MPC wallet, because it's permissionless wallet which controlled fully by Ihor Canister, and nobody can like access it or in different ways. So you can just like top up this wallet and for gas execution, and it will be delivered for you. Also, we have like request-based mechanics that on top of you can just like from your Solidity contract you can request some data, and it will be delivered to your like callback on your smart contract. So in this case, actually, we are utilizing like logs, get logs through EVM RPC Canister. So on Apollo coordinator, it's like smart contract on Ethereum, for example, and when some another contract asks for some data to this contract, it just generates an event, and then we're an RPC or our Canister asking like every sometime EVM RPC Canister to check the logs of this Apollo coordinator of Ethereum, and when we see some request, we like create a transaction, like fetch this data, create transaction, sign it, and deliver to asked contract. Also, yeah, it's and in the meaning of architecture, like so, it's a like fetching mechanics, like which our fetching module. So with the meaning of EVM RPC Canister, we deliver like verifiable on-chain data. So we have like different exchange rate Canister and custom data feeds, but in the meaning of EVM RPC, we utilize it for our CBIL Canister, can get through EVM RPC Canister data from different blockchains. So it could be utilized, for example, one of the use case when you need your like some DEX on any EVM chain, and you need to like make it tradable, some recently launched token on Uniswap v2, and you don't have like any Oracle cannot provide like recently launched price feeds of new tokens. But through these mechanics, we can provide that you can ask exactly like this pool of liquidity on Uniswap recently launched. Can you provide this price feed from this data? And we're fetching it. We are reading a contract through EVM RPC Canister from Uniswap, getting it on Sibyl Canister, then generating a proof, and already it could be utilized by different third parties who can provide to your contract and verify it. Then yeah, it's as an example, we like user can dynamically fetch any type of data through EVM RPC Canister through different chains. It could be get logs, read contract, transaction receipt. So you can utilize it for some DAO application. If you need to, if you want to make like people voting power on different chains, but doesn't matter from on which chain they holding some tokens, or making a snapshot of utilizing this voting power. So person can vote on Arbitrum but holding some tokens on Ethereum, just for simplifying and making it less costly. He wants to execute vote on Arbitrum, and you can allow him to do it by reading a contract from Ethereum, understanding that exactly this address holds something, some tokens on Ethereum, but and this proof could be allowed to be used on Arbitrum contract. In the meaning of PT automation tool, it's EVM RPC Canister utilizing when we already got like data and prepared transaction, and when we send it to already like chain where like destination contract, it's a signed transaction sending to this JSON-RPC API send row transaction, and it's delivering. And it just like how already mentioned, our Apollo things working. So it's we have a like consumer contract, we have Apollo coordinator. When consumer asking some price feeds or any type of data need to be delivered, Apollo coordinator triggers some events, and then we are listening through EVM RPC Canister like different logs which happened on exactly this contract on one chain, and then execute it to those chains. And in general, yeah, I wanted to mention that this really allows you to do a lot of different things in cross-chain communication and in a chain fusion way. So yeah, it's just our information, and that's all from my side. So thank you so much for your attention. If you have any question, I would love to answer.
For those of you that are wondering, recordings of that session will be made available in the next 12 hours and published within the Hacker Pack, as well as a copy of the presentations of both Grégory and Ihor. So don't worry about this. If you're seeing any link that you might have missed or small detail on the screen, we will make sure that these are made available to you as quickly as possible. I'm not seeing any new questions, so Ihor, maybe some closing words from your end?
Yep, sure. So as I mentioned, it's a really cool thing that DFINITY building like some simplifying like management canister as exchange rate canister for providing real world data, and this EVM RPC canister which allow you more easily to interact with EVM chains. It's really like cool and simplifying, utilizing like onboard new developers, and for new developers it's really much easier to make those interaction works. So not in just a potential and technical things that potentially I can do it, but in the real practice and you can just start, and it's much easier to start.
Amazing. To continue to round things off at the end, everyone, please be aware that we are currently in the second week of the hackathon. We still have one more workshop ready for tomorrow, and by the end of this week, we'll be expecting all of you to submit your idea submission, which is basically a short description of what you're planning to build, which can give us a heads up on everything that you want to achieve for this hackathon, and we will be able to then identify the best way to support your developer journeys and make sure that all of your ideas come to fruition and you end up submitting a project for that idea. So think of it, think on it, and we will be sharing the adequate links for you to submit your ideas by the end of this week. Finally, thank you again, Grégory. Thank you, Ihor, for your presentations. For everyone else, if you have any questions, make sure to post them on our Discord, and we will follow up afterwards. Thank you all for being here, and wishing you all a great day.
Thank you so much. Have a good
Bye
day.
all.